Welcome to another episode of Traveling Through Space. And I'm delighted to welcome Dr. Oliver Jennrich, LISA study scientist. Oliver, welcome to the show.
Yeah, thank you. I'm happy to be here.
Awesome. And I really appreciate the European Space Agency making this happen and giving me the opportunity to talk to you today. We have a lot to cover. And I was hoping we could start with, briefly with your journey to becoming the study scientist on LISA, which is the Laser Interferometer Space Antenna. So if you don't mind sharing just highlights of your journey through here.
Yeah, it has been, first of all, it has been a long journey. So I studied physics in Hanover in Germany. I was always interested in kind of natural sciences, or STEM as you say it today, but actually picking up physics then after school was kind of a spur of the motion idea. So there were other options, but I looked through some classes and thought, oh, that's interesting. So I went there. And then I did in these days, we still did diplomas, not masters or bachelors. I did my diploma in physics and a theoretical physics topic also in Hanover. I then switched over to experimental physics again in Hanover. So I was relatively static at that point, but I switched topics, so that was kind of exciting. And the main thrust of the institute I was working in was always gravitational wave detection, but we were all focused on the ground-based detectors like LIGO and VIRGO and the prototype we had in Hanover, GEO 600. And there was a day when my then boss, Carsten Dunsman, came and said, here's another diploma student who wants to do something about LISA. And he looked at me and said, Oliver, you know how to calculate these things. Why don't you take care of that student? So that was my first connection with LISA. That was 1995 or so. And since then, I have been working on and off with LISA or ground-based detectors. So I finished my PhD thesis, which was mostly about advanced technologies for ground-based detectors and investigating quantum mechanical limitations. And then I went to the US for a postdoc. I worked with Chuck Stebbins and Pete Bender at the University of Colorado for 2 years on LISA. Then I came back to Europe, to Glasgow. I worked on ground-based detectors again. And then in 2002, that's more than 20 years ago, the European Space Agency announced that they're looking for a study scientist for LISA. So I thought, hey, that sounds cool. Applied, and apparently I convinced people enough to hire me. And since then, I've been working on LISA. Programmatically, LISA had a couple of setbacks in the agency because other things were more ready to fly, to be honest. We didn't really have the technology. We also had to then decided to fly LISA Pathfinder. I was heavily involved there as well. And then over the years, we had a couple of studies on LISA, industrial studies, to look how to actually build that thing and what technology you need to do to actually develop to actually be successful. Yeah, unfortunately, last 2 weeks ago, our science program committee admitted us fully into the program, which means that, internally, or the official term is we got adopted, but for all practical purposes, it means we now have a solid budget that brings us through to launch and operations. So we know how much money we have available to build the 3 spacecraft, launch them, and operate them. And since then, we kind of progressed from a study to a project. So that's the big milestone.
Awesome. Yeah. And this timing of this interview could not have been more fortunate, just right after that big news
Yes,
that's
indeed.
Celebrated across the world. So yeah, that was a wonderful overview. Now, just to level set with a brief introduction or just high level introduction for the core concepts that are needed to understand LISA, and I'm sure you have thought about it and you probably explained it many times to different user groups. So I was just wondering if we can start with perhaps space-time, and if that's a concept to begin with.
Yeah, this is space-time. Yeah, this is a concept that, I mean, probably most of your listeners will know has started by, or invented by Albert Einstein in the early 20th century when he formulated his general theory of relativity. And the concept really is not usually seen more mystified than it is. It simply means that in this theory, we cannot, as Galileo did, say, I have space, you know, in which bodies move, right? The famous balls that fell off a tower or whatever, right? And we have time, that is a parameter that just effectively is something you read off your wristwatch, right? So you know this ball takes 1 second to fall to the ground. So you can parameterize the fall by saying, where are we? Now, space-time is the concept that it's not that we have space on one side and time is a completely different parameter, but they all play effectively indistinguishable roles in the description of the dynamics of bodies and also in the description of gravity. So, and the key concept there is that the speed of light is finite and constant. And as soon as you have that, you can easily imagine situations where you say, well, you know, two people might share the same birthday, or two things happen at the same amount at the same time, right? Two bells are struck at the same time or something like that. But if you have a finite speed of propagation, you can easily construct yourself situations where things are simultaneous in one coordinate system, but happen at different times at a different coordinate system. And right. So once you realize that, you say, hang on a second, time is not just a parameter that describes things, but time is a coordinate. And that's there all days, right? And if you know how to deal with coordinates, you can effortlessly deal with 4 instead of 3 coordinates. It's just a change from our everyday experience, because most of us never experience time as a coordinate. We all experience it as a parameter. It tells you when to go to lunch, right? Or to go to sleep or whatever, but you never consider it as a coordinate. Like you say, well, I'm now sitting on the couch, right? Or I'm now sitting in my car, or driving with my car to somewhere. These are coordinates, but yeah, it's just a small shift in your everyday life or your everyday experience, and that's all there is.
Yeah, that makes sense. And then you make a little leap towards gravitational waves.
Yeah,
that sort of come out again with Einstein's work.
This is also, yeah, this also came out of Einstein's work quite naturally. And again, if you look into why do we have gravitational waves? And before we even start thinking about what is it, how do they manifest themselves, it's almost inevitable if you have a theory which with a finite propagation speed of something, right? In this case light, or also gravity, which also propagates with the speed of light, then it is clear that you cannot have instantaneous effects, right? So if a mass miraculously appears here, you don't see the effect right away. So there is a delay. So you could see that, you know, if a mass appears or moves around, the effect shows up later somewhere. Now, if you do that periodically, you can convince yourself that, oh, there's a funny thing, right? There must be some periodic oscillation in space-time. Now, gravitational waves are effectively the extension of that. You have the equations of space-time, and if you look at that and you say, what happens if I disturb it a little bit, right? So for example, I have two heavy bodies that move around. Instead of sitting there statically, they're moving around. So they have the static solution slightly disturbed. You immediately come to the conclusion, really within a few lines of calculation, you come to the conclusion, oh, there's a wave propagating. There's a wave moving out, carrying that information away. And then it's a little bit more complicated to say, okay, how does this wave actually manifest? And there again, if you look into the math, one easy way to describe it is to say gravitational waves change distances. right? So it's not that they make you heavier or lighter, which also is a natural idea to have. And if you talk to people, this is most likely the first idea they have. Oh, gravitational waves. I know gravity. Gravity makes me heavy, so gravitational waves modulate my weight. No, it modulates your height and your width, right? So it doesn't make you heavier or lighter. It makes you wider and taller, or thinner and shorter, or whatever.
Right.
So squeeze you. And we know, if we already know from everyday experience, at least those of us who are living close to an ocean already have that experience, right? The ocean around the Earth is squeezed and stretched by the gravitational gradient of the sun and the moon. We call it tides, right? And in a sense, gravitational waves are nothing else than tidal forces on bodies. And you can say, you can have that idea, say gravitational waves create tidal forces, or you can say gravitational waves change the distance between objects. At the end, it's the same. Mathematically, it's the same. It's just, the way how you decide to mentally picture it. And if you're an interferometric person like myself, so who grew up, scientifically speaking, with the idea that you can measure distances or changes of distance with an interferometer to an extremely high precision, then of course you're looking into the question of how does a gravitational wave change the distance. If you're coming from a community that are concerned with keeping bodies as free of force as possible, to measure free fall, for example, then your gravitational waves are exerting tidal forces. And in LISA, we have to marry both concepts. As I said, it really doesn't matter, right, how you think through that, as long as you do it correctly and stick to your guns. If you change the pictures halfway through, madness lies that way, because you can get all sort of interesting knots in your brain if you think through that. But in LISA, we have the two concepts where we have the 3 spacecraft in orbit with a large distance between them, 2.5 million kilometers. And we measure the change of the distance between those satellites, or to be precisely the test masses in the center of the satellites, and to have a measurement point. And this is our signal, right? Now, we also have to make sure that this signal means something, because it's always easy, not always easy, but it's one thing to measure something. It's the other thing to actually make sure that what you measure has something to do with the phenomenon you wanted to measure, and it's not created by something else, right? So if you want to measure the distance between your chair and your desk, that's one thing. But if you want to make sure that this has something to do with reality, you better make sure that the chair isn't moving away during that time, right? Because otherwise you measure something wrong. So the object that keeps us kind of true there and tells us, yes, you're really measuring the distance and the change in distance caused by gravitational waves, and not by some other stuff that's pushing the spacecraft around. Solar radiation pressure, magnetic fields, all that. We use the so-called test masses that are, I don't know if you want to use the camera later. I have here one. This is a picture of a test. It's not a picture of a test mass. It's actually a prototype of a test mass. It's about this size, 46 millimeters, and this one is made out of tungsten, but the real ones will be made out of gold platinum. And so we try to keep them as free of any force as possible. So we make sure that they're not hit by solar radiation, by having the spacecraft around it. We make sure that the spacecraft is gravitationally balanced, so that they're not pushed or pulled into one direction. They are in a vacuum can inside the spacecraft, because believe it or not, the vacuum in and around a spacecraft is not good enough, because the spacecraft has stuff, and stuff releases gas, and that gas we don't want. So we have it in a nice vacuum system, We make sure that we don't touch it. If we control the distance of the spacecraft to that test mass. So we quite literally flying a spacecraft, a 4-meter diameter spacecraft around a 4-centimeter test mass with precision thrusters that use cold gas, so nitrogen, expelling nitrogen very carefully to nudge the spacecraft around so that it doesn't collide with that test mass. And but these are effectively our way to say, yep, we are measuring gravitational waves, right? Making sure that the signal we are measuring is caused by gravitational waves and not by other stuff.
Right, right, yeah, and I can only imagine the amount of technical discovery that needs to happen, the scientific process that needs to go through to even think about it. You actually answered a lot of my questions, so really appreciate that. that answer sort of it flows through and ties multiple questions that I had, at least in my mind. If you could take a step back towards the ground-based observatories, as you mentioned, LIGO and VIRGO. LIGO being the Laser Interferometer Gravitational Observatory, which successfully detected the gravitational waves in 2015. And I was just curious about the current precision levels, and some of the limitations that you look into.
So, I mean, first of all, the principle we are using for detecting gravitational waves with LIGO, VIRGO, also the Japanese colleagues Kagura and LISA are essentially the same. We are looking into the question, how does a gravitational wave interact with light and how can we measure that? Now, the difference between LISA and the ground-based detectors, let's start with the fact that the ground-based detectors are much, much, much more sensitive than LISA. LISA is designed to measure changes in distance of picometers, so that's 10 to the minus 12. Ground-based detectors routinely are 7 to 8, maybe even 9 orders of magnitude more sensitive. So they're measuring 10 to the minus 20 meters. They have to, because gravitational waves, one effect of gravitational waves I didn't mention, I mentioned it changes the distance, but what it also is, it's a fractional effect, which means that the longer the distance is, the bigger the change. Right? So this is why LISA goes for 2.5 million kilometers. It's an enormous distance. And the gravitational wave comes in and changes that by a handful of picometers. Right? Now, the same gravitational wave, not the same, but of similar strength, it turns out they are roughly all, by some happenstance, have a similar amplitude when they arrive here. On a kilometer-sized detector like LIGO or VIRGO, like 4 kilometers, 3 kilometers, whatever they actually are, is that you have to measure much, much better, to a much higher precision to capture the same amplitude. So the ground-based detectors are way more sophisticated, employ techniques that are not even imaginable in space, right? Because partly because they need human interaction to make it work, right? So they have people there that they can send and say, well, something isn't working over there. Can you tweak that a bit? Now that's difficult in space, right? You can't deploy your postdocs there. Ethics committee has something to say about that. We can't do that. So, but on the other hand, the ground-based detectors are by obvious limited in size. You can't fit 2.5 million kilometers on Earth. You barely can get a couple of thousand kilometers, and practically you're limited to a couple of kilometers. Mostly, not part of the reason is that light goes straight and the Earth's surface isn't, right? So it's a sphere. So there's a limitation to that one. The ground-based, because of the shorter arm length they have a different frequency observation window compared to LISA. So one of the things is that because gravitational waves are periodic and they are shrinking and squeezing, the distance, You can imagine that when a full wavelength fits in, or half a wavelength, and the light goes back and forth, the effect cancels, and that's exactly what happens. So if your arm length, the distance that you're measuring, becomes too long, you become insensitive to high frequencies. Now, the ground-based detectors all aim at what we call acoustic frequencies, so a few hertz to maybe a kilohertz. Now, and that tells you that you cannot be terribly long, otherwise you are also canceling the effects. The question is, why are we looking at that range? Is because when LIGO and VIRGO were designed, or the first concepts were there was a strong hope that we will see supernova signals. And supernova signals in gravitational waves are like a bursting balloon. You hear a sharp bang, and that sharp bang has kilohertz frequencies, and it's relatively broad band. But if you have a sharp signal, then it contains a lot of different frequencies. And so the ground-based detector says, well, if I can go up to a kilohertz and maybe down to a couple of hundred hertz, I will see some supernova. Now, in the meantime, after many, many evolutions, they managed to get their low frequency sensitivity better and better and better. And so now they are seeing routinely signals with 100 hertz or below. But there's a limit. You can't, on ground, you can't go much below a few hertz. I mean, maybe you can go to 1 hertz if you do really, really fancy stuff, maybe even lower. You never go to millihertz, right? And that has to do with not so much with technology. It's not that you can't build machines that would be sensitive in that way. It is more the second half of the problem I told you about, making sure that what you're seeing are gravitational waves and not cars moving by, ocean waves hitting the beach, weather patterns passing by. I mean, millihertz is 20 minutes. A lot happens in 20 minutes. A storm cloud can pass over in 20 minutes, right? A rain shower passes over in 20 minutes, and a rain shower has a lot of mass, right? I mean, a single raindrop doesn't, but a lot of them, right? And it has a Newtonian effect. It pulls on your mirrors, right? And it looks as if it's changing the arm length a bit, and it looks like, well, maybe it doesn't look like, but it certainly gets in your way in detecting gravitational waves. There are other things, I mean, things that you simply cannot control. And in contrast to our radio wave friends or electromagnetic observatories in general, there's no way to shield against gravity, right? That's one outcome of Einstein's general relativity, that kind of gravity is universal. You can't really shield against that. And that then creates a problem if you have a lot of noise sources around you. So one of the reasons, certainly the main reason to go to space, is if you want to observe low frequency gravitational waves or lower frequency gravitational waves, you have to go to space. Because there at least you're free from things like weather, people, oceans, all that. You have other problems, but you can at least try to control them. If you go to very low frequencies, to say nanohertz, so things that happen on timescales of many years, right? Then you can go back to ground again, but you're still using a space-based effect. You're using the traveling time and the arrival time of pulsar sequences that are crossing space, affected by gravitational waves. And it's just that you register them on ground with your radio telescopes. And this is what the pulsar timing people do. They are living in yet another frequency space, right? So you say ground-based is acoustic, let's say a few hertz to maybe a kilohertz. Laser from a few hertz, maybe down to a tenth of a millihertz, so time scales of 10,000 seconds, and so a few wave cycles during a day, right? And pulsar timing has, a wave per year and a wave cycle per year, up to maybe a wave that lasts for 30 years. So it's very, very low frequency. And
right, right. Fascinating. Yeah, and I was reading Jenna Levin's book, The Black Hole Blues, of the
yeah,
story about how LIGO got built, and it talks about pest control being one of the issues where the black widows, snakes, and whatever will creep
yeah,
into the tunnel, and definitely our world is dynamic, and
yeah.
we're sort of shielded from that in the space. So yeah, that was
Indeed,
wonderful.
we don't have rodents. I very much hope so. We don't have mice who decide that it's a good idea to shorten out the high power lines, and they do that only one. Well, any individual mouse does it only once, but it's annoying enough, right? And you
Right.
also wonder about the concept of a clean room that houses a family of mice, but if you're out in the field, and LIGO and also GEO were built literally in a field, right? It's
Right.
not like a super clean environment that you can completely control, right? So it is. It's
Yeah.
not just lab physics. It's field physics, indeed.
Yeah, absolutely. If you have few more minutes, I
Yeah,
have
sure.
a few more passing questions. The next question I was interested in was just knowing the overall timeline with NISA, some of the milestones that you're looking forward to now.
Yeah. So when we went to our science program committee and asked them to adopt LISA, we told them that our planned launch date is August 2035. So this is where we are. Now, in between now, where we start building, well, we are not starting building yet, but between now and then, a couple of things have to happen. So the first thing is what we're preparing now is what we call the invitation to tender, because ESA is not building things. We are giving money to European space industry to build things for us, and to national institutes. The national institutes also get their money from national funding, of course. But the big chunk of money goes to European industry. And of course, we're not handing it out like that. We invite them to submit a tender. They will submit a tender, and then we are picking what we call prime contractor, that then will be kind of the overall architect of the mission.
Mm-hmm.
And then programmatically, we have a couple of other steps. We have to make sure that the design is sound. So we will have a preliminary design review. We have a critical design review, after which really cutting metal will happen, right? So for the next couple of years, it is there will still be a lot of paperwork involved, and also we will start testing the critical technology that's not fully up to notch yet. We say, well, we have to better look into that problem again, and maybe we have to run a test campaign with this little bit of hardware in a test chamber and all that. So I don't know the precise dates when these reviews are planned, but then a big chunk of time is due to the fact that we have to build 3 spacecraft, right? And you can only parallelize these things to a certain extent, because if you fully parallelize them, then you have to build your infrastructure in triplicate, not only the spacecraft, but also the infrastructure, the rooms in which they are built. You have to build up 3 teams that do that in parallel. And one can do that, but it's vastly more expensive. So there's always a compromise between we want to get it done in a finite amount of time, but we also don't want to spend, an insane amount of money on things that can be done slightly cheaper. So this whole idea of 11, 12 years from now to launch is partly driven by these compromises we have to make. Say we have to build 3 spacecraft, and we have to test things, and we have to make sure that it works in space. So there's that. But at the moment, as I said, we are looking for the mid-30s to launch. And then it will take about a year and a bit to get from Earth to the final orbit of the LISA constellation. Then we, for lack of a better word, we have a shakedown to make sure that everything works and that the constellation works and that we have the kind of ideal operating parameters. And then if everything goes fine, we'd just switch it on and contact every day to get the data down. And maybe tweak things a little bit here and there, but mostly it's not a mission where we actively steer it around and say, look at this, look at that, look at that. So we just put it there, make sure that it is happy and well behaved, and then we take data for as long as we possibly can, which anywhere between 5 and 10 years.
Gotcha. Yeah. No, that makes a lot of sense. A lot of moving parts, but it's also the way you explain it. It seems like this also will have knock-on effects on industry standards improving and technologies moving forward, which might not have.
We did a lot of the kind of critical processes and validating them for LISA Pathfinder, our technology demonstrator. I think in general, the space industry has processes extremely well under control, which also makes things for the outsider look agonizingly slow. Why do they take so long to do something? And the answer is because the last 5 times we did it faster, something went wrong, right? So we put in these checks and these tests and make sure that somebody else looks at it as well. So, and all that, and then we do another test to make sure that still everything is fine, and all that takes time. But the benefit is that when we launch a mission, it works, right? We are not in the habit of things breaking in orbit. So there's that. And yeah, the price you pay is that it takes for a while, right, too.
Right. Yeah, absolutely. Just curious to know about the ESA NASA coordination and how is that? Is that a partnership?
It is a partnership. In the dim and distant past, when we first thought about that mission, we made a kind of agreement that it's a 50-50 share, but that eventually turned out not to be feasible because of the different financial commitments that we have to do, that NASA has to do. NASA has a completely different accounting system than we have. So in other words, they have things contributing to a mission cost that are not showing up in our accounting sheets for the mission, at least. We have contributions from national member states. They are substantial in LISA, so that's also thing. So for the current mission, we say NASA is a partner, but it is clear that ESA is leading the mission. NASA will contribute hardware, like the telescope and the laser will be built by, or the lasers will be built by NASA. They will also contribute to an aspect that shouldn't be underestimated, which is the data analysis later. Right, thus the data that comes to the ground is probably, the raw data is probably unusable for anybody except the experts. So we first have to make sure that we extract the sources where we say this part comes from this guy and this part of the sky with the following parameters. And there's an effort in that one. And so, yeah, I'm not sure what the NASA allocation in terms of financial means is for LISA. It is not cheap for them either. It's a substantial amount of money, but it's smaller than the amount of money the ESA is prepared to pay, and that even doesn't include the amount of money the national space agencies that we still have in Europe, right? It's not just ESA, it's also DLR in Germany and ASI in Italy and UKSA and CNES in France and all that. They contribute a significant chunk of money as well. So it's, yeah, but this money, these are coordinated by ESA. So if you say it's probably something around 70-30 or something like that between ESA and NASA, maybe 60-40, but it's clear that ESA has the lead here.
Right. Yeah. That makes a lot of sense. And you touched upon the analytical capabilities that are needed to sort of make sense of the data coming in also makes a lot of sense. It's similar to LIGO, and I'm sure in the past in other observatories, it's been the challenge to make sense of that data.
Yeah, we have.
Well, so.
It is one of the things that all of our gravitational wave detectors do not deliver pretty pictures, right? I mean, a normal optical telescope, you can point to the sky and you can deliver that picture to the general public, and they say, "Wow, that looks interesting." Now, the real science only starts there, right? There is a lot more that goes into the detailed analysis of that particular pretty picture. But it's a pretty picture. You can show it. It's nice, right? We don't have that. But you're right. The data analysis is kind of similar to what we do in LIGO, with the exception that LIGO is essentially a noise-dominated detector. So they have noise and occasionally a signal. And you could say, well, occasionally every week or something like that. Whereas LISA will be a signal-dominated detector. So we expect the total effect of the signals be significantly higher than the noise. So that, let's say, change the focus of the data analysis a bit. It makes data analysis in one kind a little bit easier because you sometimes have extremely loud signal and the noise really doesn't get in the way. But it makes it more difficult on the other hand because you have signals all the time. You can't just say, for example, I look at the noise behavior of the detector without a signal. That's not happening. You will always have a signal, right? So the underlying, let's say, methodology is the same. But the focus is slightly different. But yeah, certainly a lot of the colleagues in data analysis are in both areas. So they do work for LIGO, they prepare for LISA. And you're right, other detectors, other space missions, if you think about Gaia or Euclid, they do and will have to do a lot of data analysis before the kind of the nice data product that the astronomer can use to do something comes out.
Right. And the image I think about is, with EHT and they physically carrying the disk around to sort of
we hope we can avoid that. I mean, there's not much that we can do when the data is coming down.
Right.
So
awesome.
The nice thing about LISA in this respect is that it's a low frequency detector. How many bits per second can you accumulate if your signals are living in a space below 1 hertz, right? It's not a tremendous amount. It's good because it's relatively far away, so we don't have a huge amount of bandwidth coming down, so we have to have huge, big antennas and all that. But the data arrives at our normal ground stations, which are not in Antarctica, which is kind of the last place on the planet where you don't have internet. So this is why they were shipping a huge amount of hard disks around, because they collected data over Antarctic winter. And you can't get the data in or out. So you have to wait until the next flight comes in spring, and then you push the crate with the God knows how many terabyte disks on there. Right? And
Awesome. Well, that was great. And I think it's a perfect example of how science sort of transcends artificial borders and serves for the betterment of humankind, of our knowledge, and just our long-term understanding of the universe.
That's certainly true. Yes.
Yeah. Well, this is all the time we had, and I appreciate you giving me time to talk to you. This is a treat for me, and hopefully we can talk again. But really appreciate you giving the time, and special thank you to the European Space Agency for giving me this opportunity as well. Any last words? Anything we didn't cover? Because we went through a lot.
I think I mean, there's lots of more things I can tell you about LISA, but given that we have a limited time, and also, we don't want the eyes of the audience glaze over even more, I think that pretty much sums it up.
Thank you, Oliver, for making this time, and it was a wonderful conversation.
Okay.
Have a good rest
Good.
of the day.
Okay, thank you.